So welcome guys. I hope everyone's day has been going well. So I guess we'll get started. So today we'll cover geometry. So personally, I think geometry really requires you to sort of have a creative approach when you're doing problems. So let's just get started, I guess. Slide. So today we'll cover some techniques first, such as angle tracing, and then we'll cover some properties for cyclic quadrilaterals, and then we'll cover some constructions, which is a very important sort of technique in geometry problems, right? So you use it basically for every problem. And then later on, we'll cover some theorems for collinearity and some theorems for concurrent lines. So I guess one of the simplest techniques in geometry is to sort of chase angles around. So what that means is basically when you set out a problem, you draw diagrams first, and then maybe you can start figuring out some angles straight away, right? So for example, if you have a square, then you can label all the sides to be right angles, or if you have like an isosceles triangle, then you can sort of label two angles with some variable alpha. And then what you want to do first is you want to try to get as many angles as possible so that hopefully you'll get some useful information and hopefully that helps you approach the question better. So when you're actually writing like a formal solution, you should always use some sort of explanation to back up each of your angle chase. So for example, if you're proving two angles are equal, you can just write in brackets in your solutions, your explanation for it. So like, because they are alternate interior angles and therefore these two angles are equal, or because two angles are from the same line, therefore they add up to 180 degrees, things like that. And the most important tip for any geometry problem is to actually draw them out. So yeah, so you're doing geometry problems, you have to, draw diagrams out, and that will make the question a lot easier. So the first theorem that I want to introduce to you guys today is the alternate segment theorem. So we'll draw this. So let A, B, C be points on a circle. We have just random 3 points A, B, and C. And let PA be a line segment such that P lies on the opposite side of the line AB as C. So line AB, so P will be somewhere here. Then the line PA is tangent to the circle at A if and only if angle ACB, so this angle, is equal to angle PAB, in this angle. So if PA is a tangent to the circle, then angle PAB will be equal to angle ACB. And if angle PAB is equal to angle ACB, then we can say that PA is a tangent to the circle. So that is a very nice property to note. And we actually have a diagram which shows this property. Yeah, it's a very useful property. So whenever you see circles and whenever a question wants you to prove that something is a tangent to a circle, you should always think of this property because it becomes very useful. Yeah, so we'll see that in an example. So let's draw something else again. In a parallelogram ABCD, where AC is longer than BD, so we'll draw that first. Parallelogram AC is longer than BD. Right, let P be a point on AC such that BCDP is a cyclic quadrilateral. So a cyclic quadrilateral is just the circle that passes through all four of these points. Right, so let's draw P. So another very, I guess, important thing to note is that for every 3 non-collinear points, there's only one circle which passes through all 3 points. So we can actually only draw one circle around points B, C, and D, which means that our point P, that's a very bad drawing, but we'll have a diagram later on. That means there's only one P on this line. So what we want to do is we want to prove that BD is a common tangent to the circumcenter of triangle ADP and triangle ADP. So a circumcircle, not circumcenter. So circumcircle will be a circle that passes through all 3 points A, D, and P. So I'll actually get rid of my drawing and show you guys an actual diagram. Yep, which will look something like this. So we want to prove that BD is a tangent to this circle from the triangle ADP. So does anyone have any ideas of how you can do that by probably using, alternate segment theorem? Right. So, and because we want to prove that BD is a tangent to the circumcircle of triangle ADP, it's kind of really an obvious thing to first try is using alternate segment theorem. So instead of proving that BD is a tangent, we now want to prove that. We now want to prove that angle BDP is equal to angle DAP. DAP is PDB. Yep, exactly. So that sort of simplifies our problem. And next, so by the alternate segment theorem, it is sufficient to prove that angle PDB is equal to angle DAP. And the second sort of equality is for the other circumcircle, which we will prove later, but it's basically the same proof, just for a different circle. Okay, and since the quadrilateral BCDP is cyclic, we also have angle PDB, which is this angle here, is equal to angle PCB, which is this angle here. Now, this is a property of cyclic quadrilaterals, which is basically saying for the same arc, which is this arc PB here, every angle that's subtended by this arc on the other side of this arc will be the same. So actually I can show you guys real quick. It's here in this diagram. So as we can see, the arc AB will subtend the same angle on every point of the rest of the arc. So if I have a point here called E, this angle will be 74 degrees as well. And similarly, if I have an angle here, that will also be 74 degrees. Okay, let's back. Oh, we're here. Yep, so what we had was this angle is equal to this angle, which is also equal to this angle. And now we can also deduce that angle DAC is equal to angle ACB. This is because AD and CB are parallel, and then you can sort of just conclude that from what we've learned in high school, that because these two are alternate interior angles, then they are the same. And because we proved that DAC is equal to ACB, and also ACB is also equal to PDB, therefore we can just draw a conclusion that DAP is equal to PDB. Right, so this angle alpha is equal to this angle, And this same alpha is also equal to this. And so all three angles are the same. Which we'll see here. Yeah, which is what we wanted to prove. Now for the other part of the question, it's basically a similar proof, which I guess, does anyone actually want to see the proof? Because it's sort of similar. Yeah, so if anyone wants to see the proof, I'll do it, but otherwise, I guess we'll just move on for now. Oops, I'll try to clear that. Okay. Now, cyclic quadrilaterals. Cyclic quadrilaterals is basically a circle which crosses through 4 points. I guess we'll have a diagram. Yeah, so these two quadrilaterals are both cyclic quadrilaterals because there is a circle that crosses through all 4 points. So there are a few nice properties with cyclic quadrilaterals, and usually they're very helpful when you're solving problems. So the two theorems are if a quadrilateral ABCD is cyclic, if and only if angle ABC plus angle ADC is 180 degrees, which you can see in the left picture. So sort of the opposite angles of a cyclic quadrilaterals add up to 180. That's a very useful piece of property that you should use in your solutions. And another property is a quadrilateral ABCD is cyclic if and only if angle ACB is equal to angle ADB, right? Which is basically what we used to solve our previous problem. So the angles subtended by the same arc will be the same. And here's another example to consolidate our understanding. So in triangle ABC, I'm gonna stop drawing diagrams because they're so bad. We have diagrams later. So in triangle ABC, points D and E are located on the side of BC such that AD is an altitude and AE is an angle bisector. So to show our diagram. So AD is an altitude and AE is an angle bisector. The point M is on AE such that BM is perpendicular to AE and point N is on AC such that EN is perpendicular to AC. So basically that's our diagram here. So what we want to prove is the blue line, that D, M, N are collinear, which means that they're on the same line. Now, it might be a bit hard to prove that 3 points are collinear, so we can sort of change that into proving something else, right? So usually what we do is we prove that angle, there's multiple ways to prove that some things are collinear. So we can prove that this angle DME plus this angle NME adds up to 180. So that's one way of proving collinear points. And also, we can say that angle MDE is the same as angle NDE, right? So MDE is same as NDE. And if they are in fact the same, then these 3 points will be collinear on the same line. So we're going to use the second approach in this question, I'm pretty sure. So on the cyclic quadrilateral theorem, we know that ABDM is cyclic because angle ADB is equal to angle AMB. So they're both 90 degrees, right? So that's the, that is the second theorem here. And can sort of, I'll try to draw a circle, but it's not going to look nice. I'll just try to do it. It will look something like this, which is not nice at all. Anyway, and this arc AB will subtend the same angle, which are those 90 degrees here. And we also know that ADEN is cyclic. So this is cyclic because ADE plus ANE, ADE, I'll just clear it and show you guys here. ADE right angle plus ANE, which is also a right angle, adds up to 180. So that was the first cyclic quadrilateral property that we had, right? The opposite angles adds up to 180. So those are both cyclic quadrilaterals, and we can use that to assist our proof. So as I said, for proving collinear points, there are multiple methods, and the method we'll use right now is proving that BDM plus NDC is 180. Why? Well, obviously, because BDM plus MDC, look, there's a different, so I'll just write it here. So obviously BDM plus MDC is 180, right? Because they're on the same line. So now if we can prove that BDM plus NDC is also 180, that means that points D, M, and E are on the same line. Okay, let's try to do that by some angle chase. So we'll first try to label BAC is 2 alpha, right? And then we'll try to label as many points, as many angles as possible. So BAE and CAE are both alpha because AE is the angle bisector of the triangle. And then more points here. So cyclic quadrilateral ABDM tells us that angle BDM is 180 minus angle BAM. So BDM, which is here. No, sorry, BDM is here. So yeah, that'll be 180 minus alpha because BDM and BAM, which is alpha, are the opposite angles in a cyclic quadrilateral. So this is 180 minus alpha. And we can sort of see that this angle here, MDE, is alpha. And also, cyclic quadrilateral ADEN tells us that NDC, all right, so here is equal to NDE, which is equal to NAE. So yeah, so I'll draw the circle again. Oops. So from our second quadrilateral property, that's a very bad circle. We can see that if this angle is alpha, which is subtended by the arc EN, we can also see that this angle is also, this angle MDE is also subtended by the arc EN, right? Which means this is also alpha. So now we have proved a very interesting thing. We have proved that NDE is alpha and MDE is also alpha. So if they are both alpha, that must mean that these 3 points, N, M, and D, lies on the same line because they both create the same angle, right? That's basically supporting what we have proved. I know that could be a bit confusing because of my poor drawing skills, but does anyone have any questions or anything that want me to clarify? Feel free to post it in the chat and I'll re-explain it by drawing better diagrams if I can.
I guess I got one thing. I think for these types of questions, try to be careful not to accidentally assume what you're trying to prove. For example, in the diagram, D, M, and N already look collinear, so you might accidentally try to use the fact they're collinear before you've proved it. That could be one pitfall for these types of questions.
Yeah, that as well, which I might have accidentally did. I don't think I did, but yeah, anyway.
I think maybe might be good maybe not to have the maybe in your actual diagram you can delete the blue line, for example, to remind yourself you haven't shown the error line yet.
Yeah, that's obviously a nice thing to do. Thanks, Yasser. We'll move on to the next example. There's one more example of angle tracing. So let ABCD be a square and P be a point on its side BC. So try to draw it nicely. So A, B, C, D, and P is somewhere here. The circle passing through points A, B, P intersects at BD once more at point Q. So there's a circle which passes through these 3 points, intersects at BD once more at Q. Circle passing through points CP and Q, right, CP and Q, intersects BD once more at point R, which is here. Now, this diagram might look super messy. So what we want to do is we want to sort of draw a part of it first and try to see if we can get any information out of a section of this diagram. And then we'll try to finish our diagram and see if we can get more information. So here is a section of this diagram. So we'll first try to examine things here. And by the way, what we want to prove is that A, P, and R are collinear, which R isn't even on this diagram yet, but it will, we'll draw it later on. We'll try to see if we can do anything here first. So since BD is a diagonal, we can say that ABD is equal to CBD, which is 45 degrees. So always try to label your diagram nicely, because that might help a lot. And clearly AB PQ is cyclic because that's how we constructed the point Q. So we also know that APQ is equal to ABQ, which is 45. Should be very sort of intuitive by now. And angle PAQ is also 45. Right? So this angle is equal to this angle, and then this angle ABQ is equal to this angle APQ. All right. So now, labeled it. So I'll just get rid of mine. Now we'll try to do some angle tracing. So, and some other angles that we can get from this diagram is that BQP is 90 minus alpha. Right, this is because angle this is really bad. Right, this is because this angle ABP and this angle AQP has to add up to 180 degrees. So if you do 180 minus this angle 90 minus alpha, you get 90 minus alpha. And also angle QPC is equal to 135 minus alpha. So QPC is here. So obviously you can get that from 180 degrees minus BPQ, which is 135 minus alpha. All right. Now we want to draw CQ in. It's sort of a little construction to help. And then everything, okay. And then we can get that AQ is equal to CQ by proving ADQ and CDQ are congruent. So because DQ is a common side, and then AD is equal to DC because the whole thing's a square. And then angle ADQ and angle QDC. So these two angles are the same. This is a common side. These two sides are the same. We can prove that ADQ and CDQ are congruent. So AQ is equal to CQ. And then we get AQ is equal to CQ, which is equal to PQ. Right, so PQ is here. Right, this is because these two angles are both 45 degrees, and therefore this is an isosceles triangle. So AQ is equal to PQ, which is equal to CQ. So we get this angle here is also 135 minus alpha. And now it gets a little bit messy, but just try to follow and remember what we did. We now have PCR, that could get really, really messy. PCR, the angle here, is equal to PQR, which is 90 minus alpha. We have proved that this is PQR is 90 minus alpha before. So because this is a cyclic quadrilateral, PCR is also 90 minus alpha. And since PCQ is 135 minus alpha, which we have proved in a previous slide, we have that this angle RCQ is 45. Now, because RCQ is 45 and RPQ is 45, right? Again, cyclic quadrilateral properties, and RPQ, and we have shown before that APQ is 45. And therefore, because this angle is the same as this angle, that means A, R, and P must be on the same line, which means they're collinear. Right, so basically this question and the previous question showed that if you want to prove 3 points are collinear, it's very nice to prove that those 3 points with another point will make the same angle, right? So in this case, it's very nice to prove that RPQ is equal to APQ. Okay, constructions. So construction is basically how you solve most problems. So we had one construction in our previous example by proving 3 lines are equal length. So some nice constructions are like making parallel lines. In that way, you can sort of get some equal angles going. So using like alternate interior angles. And then connecting 2 vertices that aren't already connected. That is very useful as well. I guess there are a few more which are nice, which we will see in this example. So suppose that ABM are points on a circle such that M is the midpoint of arc AB. Right, so circle A, B, and M. So M is the midpoint of arc AB. So basically MA is equal to MB. And let CB an arbitrary point on the arc AMB such that AC is longer than BC. So which means C is somewhere here. And let D be the foot of the perpendicular from M to AC. So D will be here. Right? It's always nice to draw some nice diagrams. So now we have to prove that AD is equal to DC plus CB. So AD is equal to DC plus CB. Now this could be really hard to prove because on the right-hand side, we have 2 different lengths. So what we will try to do is we'll try to sort of combine the 2 lengths on the right together. And we can do that by doing a construction. So we constructed a point P outside of a circle such that P is an extension from the line AC and CP is equal to CB. Right? So this gives us some sort of interesting properties that we can work with. So we know that CBP will be an isosceles triangle, which is really nice. So we can sort of see that this angle is also X and this angle will be 2x. This will be really nice when we're solving this problem. All right. So yeah, so instead of proving AD is equal to DC plus CB, we now only have to prove that AD is equal to DP, which is only one length. Then we will know that M lies on the perpendicular bisector of AP. Right, because D is the bisector and DP and MD are perpendicular to AP. Since M also lies on the perpendicular bisector of AB, it must be the case that M is the circumcenter of triangle ABP. So because M is the midpoint of the arc AB, you can sort of see it by symmetry that this will be the perpendicular bisector of AB. Right, so now all we have to do is we want to prove that M is the circumcenter of triangle ABP. So, yep. So I just erased everything. Oops. So we know that this is x and this is 2x. And then because ABCM is a cyclic quadrilateral, this angle here, oh, it's not this angle, not this bit. This small angle here, sorry, A and B will also be 2x, right? And why is that useful? This is because we can now draw a circle which passes through these 3 points A, B, and P. Very nice diagram, I know. And because this angle AMB is 2x and APB is x, this is 2 times as the angle APB, which means M will be the center of this circle, right? So this is also a very nice property to note. So the angle subtended by an arc of the circle at its center, M, is twice the angle it subtends anywhere on the circle's circumference, right here. So 2x is twice of x, so M has to be the center. And then we sort of know that AM will be equal to MP. And we have, wait, actually ignore that. That's basically what we have to prove. So we want to prove that M is a circumcenter of triangle ABP, and we have proved it with this property. And therefore, MD splits the isosceles triangle AMP into 2 congruent triangles, and therefore AD is equal to DP. Yep. So we basically did this question by doing a very nice construction, which combined 2 separate lengths into 1 length. And that made our proof a lot easier. And move on to reverse constructions, and I'll pass it on to Odin now. If you guys have any questions, just post it in the chat and I'll be answering them.
Great, thanks, Gordon. Good stuff. Yeah, so reverse constructions it's a special case of constructions where you're adding something to the problem to make it simpler, which is a little strange. But the idea of reverse constructions is you have some assumptions in your setup about some properties satisfied by, a point or a line, that kind of thing. And you're trying to show that with these assumptions, you can prove some other set of properties satisfied by a point or a line, or whatever. And in your setup, if you have, for example, a point with some properties and it's the only point that can have those properties, and also the properties you're trying to show, you know that if there's a point that satisfies them, it has to be unique. Well, if you can show that those 2 points are the same, you've shown that property A implies property B. So maybe we'll move on to an example of this and we can see how that works. So we've got a point in a square and its angles made with the corners of the square, the edges of the square. are 15 degrees. And we want to show that it forms an equilateral triangle with one of the other sides of the square. If we move on to the diagram, that might be a little clearer. So we're going to try to prove this without using any trigonometry or anything, just a purely synthetic constructive argument. So we've got this point O in the square, and we're making the assumption that, let me draw on here. So we're making the assumption that this angle here and this one here. So if we have a different point O, we're saying that OAB and OBA, these angles here are going to be 15 degrees, and this O is different to this point E. So we want to show that OCD forms an equilateral triangle, and there's only going to be one point inside this square that forms an equilateral triangle. Let's call it E. So we've got this new point E that we've introduced. This is a construction. And we know that because it's an equilateral triangle, it's going to have 60 here, 60 here, 60 up here. And because these here are 90 degrees, well, this is going to be 30, this angle here. This one's going to be 30. And if we angle chase around a little bit, we can see that this up here is determined by this EBA and EAB. These angles are determined by the fact that this is equilateral, and they have to be 15 degrees. And so because there's only one point in here that forms a 15-15 triangle with these points AB, and that point is E. But we also know that point is O, because that's what we assumed about O. And so by introducing this new point E that has the property we want to prove, and showing that it's equal to the point we initially started with, we've shown that the point we started with also has the property because it's the same point. Does that make sense? Does anyone have any questions about that? Otherwise, we can move on. Awesome.
Okay, that's collinearity. Okay, so in the previous examples, we saw ways of proving 3 points are collinear. So you can either prove the angle, if you have 3 points ABC, you can either prove the angle ABC is either equal to 0 degrees or 180 degrees. So for example, there's the annotation. I can draw straight lines. Yeah, so for example, if, oh no. Oh, it's disappeared. For example, if B is between A and C, can prove the angle is 180 degrees, but you have a slightly different configuration, such as like this. You can, in fact, instead just prove it 0 degrees. So AB, oh wait, not quite that. You can prove ABC is 0 degrees, such as in this picture. So they look almost collinear, but somehow you manage to prove this is actually 0 degrees, then A has to be on side BC. I've got a example question for collinearity. ABC and AD are two similar triangles, and the vertices are labeled clockwise. Now, what that means is, you've got a diagram here. So vertices labeled clockwise means if you go around clockwise, you go A, B, C in that order, and anti-clockwise would look like this. So that means going A, B, C would mean going anti-clockwise around the triangle. And now P is the intersection of the circumcircles of the two triangles. And so one of the intersection points is A itself, but we're looking at the second intersection point, and we'll call that point P. And the question is to prove P must be on the line connecting B and D. So one interesting part about this question is the vertices must be labeled clockwise. And the reason they have to be labeled clockwise is when we're doing all the proofs involving angle chasing and similarity later on, turns out that the angle chasing only works when the two triangles are oriented in a similar way. So it means you can rotate and stretch one triangle to get the second one. But if they weren't oriented in the same way, then you would need a reflection as well to get from one triangle to another. And if you had triangles opposite in oriented in different ways, the angle chasing doesn't quite work. So the problem doesn't turn out to be true. It turns out to be false. So I can begin the angle chasing. If we have a look at angle BPA, now there's two circles here. So the two circles will give us quite a lot of cyclic quadrilaterals. If we start with BPA, we can see the angle BCA is subtended on the same arc as BPA. So this is using this circle over here. We get BCA over here. And now DPA is also the same as DEA. And it's because we're using this circle now. And again, we have subtended on the same arc. Okay, and let's see. Oh yeah, so you can also use the fact, so BPA and DPA are the same as well because D is on the line BP. Again, we can use the cyclic quadrilaterals ABCP. Oh, wait, hang on. Wait, made a mistake. We're trying to prove P is on the line connecting D and D. So apologies for that mistake. So I might redo some of the explanation. Okay. So I think this is the same pitfall I mentioned earlier, where you might accidentally forget what you're trying to prove. When you see that blue line, you might be tempted to just use. You might be tempted to already think you've already proven their collinear. So maybe that's why it might be good to just rub out a line completely. Maybe draw them so they look crooked, so make them not look collinear as well. That could be a second option. So BP, so another careful part we have to be careful is you can pretend BPA is now a completely different line. So BPA is still the same as BCA. And now BCA. Now we can use the similar triangles ABC and ADE. So using the similar triangles ABC and ADE, the angle C and the angle E must be the same. So angle, that's equal to angle DEA now. And now angle DEA is the same as DPA. So this proves that angles BPA and DPA are the same. And now this finally proves that the 3 points are collinear. So P lies on the line through B and D. Okay, so diagram dependence. So it turns out we are not done yet. So diagram dependence, it means when, so as maybe to start with an example, if I say that 3 points lie on the line ABC, could be different orders of the points being on the line. For example, we'd have A, then B, then C. B could be at the middle, but we also have A at the middle, or even C at the middle. So sometimes the information given in the problem, there might be lots of different minor changes in the diagram that could exist. So there's actually more than one way of drawing this diagram and still satisfies the information given in the problem. So in this question, an example is if triangle AD was rotated clockwise until until D is beyond P. So an example is if you could have P could be here, and D could be here. So now the points B, P, and D are they're in a different order on the line, and the proof we had doesn't quite work because here DEA and DPA were the same in the original proof, but now in the slightly changed diagram, DEA is of so that's B. That's E would be, if E was somewhere here, for instance, then DEA would actually be, DEA would be 180 minus DPA, because before you had angles subtending the same arc, but now the angles are subtended, they have just opposite angles of a cyclic quadrilateral, which add up to 180. So you went from two angles being equal at the start, but now you have two angles that add up to 180 degrees. So it turns out 99% of the time, even though the diagram slightly changes, the problem is still true. So for example, equal angles might turn into 180 minuses and so on, but usually the end result you're trying to prove is still true. So as an exercise could be to try to find different configurations for this problem and trying to solve it in each of these cases. Also a technique, I think it's not in this workshop, but it's a technique called directed angles, and that helps deal with so instead of using multiple cases, there's something called directed angles that enables you to solve to put all the cases into one and solve all the cases at the same time. And that maybe a brief explanation is directed angles is you take into account whether the angle is going clockwise or anti-clockwise. So angles can also be negative in directed angles, and so this allows handling all the cases at once. So an example, maybe a quick example, is if you had ABC going clockwise here, the angle here in directed angles is the negative of this angle. So now ABC goes anti-clockwise, and in directed angles, you assume these two angles are actually negatives of each other. And you have two supplementary angles, ABC and ABD. Here, ABD and ABC are actually the same angle in directed angles rather than adding up to 180. So you're actually looking at the angle between two lines rather than, you can probably think of it as angle between two lines. So the angle between AB and, you can think of it as angle between line AB and line CD in directed angles. I guess that's a brief, yes, I guess Odin has put some further reading on directed angles. So that's a link which you can have a look at. Okay, I think, yeah, we can move on to the next section, which is how Menelaus's theorem is one theorem you can use to prove 3 points are collinear, and it involves 3 points on different sides of a triangle. Okay, so X, Y, and Z lie on, so possibly extended means they could lie within the side, or they could also lie outside. They could be outside the side as well. And put them on sides BC, AC, and AB of the triangle. And points X, Y, and Z are collinear if and only if. So if you place points X, Y, and Z like this, these points are collinear if and only if and only if this AZ over ZB times BX over XC times CX over CY over YA is equal to -1. So it's quite interesting because might ask, why can side lengths multiply to give a negative number, which such as -1? And the reason is we're making the segments having directed length. Kind of like the directed angles, which I mentioned. In directed lengths, you also take into account the orientation of the side lengths. So it's kind of like vectors, I guess, because vectors have magnitude and direction. And here, it's not quite using the full force of something like vectors, but you're taking into account which direction the line segments are going in. Okay, so an example is down here, so of direct length. So if AZ and ZB are going in the same direction, so it means the ratio AZ over ZB is taken to be positive. So again, that's like vectors going in the same direction. So the ratio we say is positive. However, if A and Z and B were here, for example, then AZ goes this way, but ZB goes this way. So they're going in opposite directions. So you can take that to be a negative ratio. Okay, so that is Menelaus's theorem. So I might quickly say, let's have a look at the example here. So suppose ABC is a triangle with circumcircle. Okay, so we find the circumcircle of triangle ABC and the tangents of, we extend the tangents. So the tangents of A, B, C, make the opposite sides at X, Y, Z respectively. Prove X, Y, and Z are collinear. So let's see the diagram. Okay, so the tangent at A meets BC at X, tangent at B meets, the tangent at B meets, tangent at B meets AC at Y, and the tangent at C meets AB at Z. So triangles XAB and XCA are similar. And this is, this uses the alternate segment theorem from which we saw at the beginning. So we have these two angles are the same. And also this angle is also common. So we have XAB and XAC similar. So this gives us, using similar triangle ratios, we have XA over XC equals XB over XA equals AB over AC. Yep. So we get 3 ratios from the similar triangles. So now we can use which equation is it? So XA, so BX over XC. Have a look at this equation. Oh yeah, so what's happening here is we're multiplying these two equations. Multiply these two equations, we get bx over xc, but that's the same as taking the square of ab over ac. And also, another thing is we're using directed lengths here, so xb has been, the direction has been flipped, so the direction has been flipped to bx. That's why we have a negative sign here, so that this is in preparation for using Menelaus's theorem later on. That's, so get bx over xc is negative ab squared over ac squared. And in fact, we can use a similar argument. So we've done bx over xc, but we can again do the similar triangles and the ratios to get az over zb equals negative ac squared over cb squared, and cy over ya is equal to negative bc squared over ab squared. Okay, how we get, so these equations are quite nice because they involve the sides of the triangle squared, and we try to apply Menelaus's theorem. Turns out you have to multiply stuff, these ratios together. And nice thing here is on the right hand side, the ab squared here cancels out with the ab squared here, and if you multiply them all, they all cancel out, and you're multiplying, you have three negative signs, and that gives you -1. So if you multiply the ratios here, we get -1. And this is identical to the statement of Menelaus's theorem from the start. So by Menelaus's theorem, you get xyz collinear. Another thing is, you can also have try proving Menelaus's theorem if so Menelaus's theorem, it's a fun exercise to try to prove Menelaus's theorem. So one way involves using the ratio of areas of triangles. I think that's probably the most common way. Another way, I believe another way is to drop perpendiculars, and you can use similar triangles. So you can see if you can come up with a proof of Menelaus's theorem. And again, there's might be a bit of diagram dependency here, which was mentioned last time, because sometimes you can have sometimes all three of the points can be outside the triangle like this. Sometimes all the points can be outside the triangle, but like here in this case, all of the points are outside the triangle. But in that previous slide, we only had 1 point outside the triangle and 2 inside the triangle. So turns out Menelaus's theorem works in both cases, and that's because of the directed lengths. Okay, now move on to Shaver's theorem. Now it's quite related to Menelaus's theorem, but now we're proving concurrency instead of collinearity. So we're proving, again, we're using directed lengths again. So if I have triangle ABC and I have points x, y, and z, it turns out they all intersect at one point if and only if these ratios all work. So az over zb times bx over xc times cy over ya is equal to +1. So again, we have directed lengths here, but instead of a -1, we now have a +1. That's the main difference between Shaver and Menelaus's theorem. Okay, so I've got a problem. Outside triangle ABC, we construct points K, L, and M, where MAB equals LAC. Angle MAB and LAC are the same. Angle KBC and MBA are the same, and angle LCA and KCB are the same. To prove three lines, AK, BL, and CM are concurrent. Got a diagram here, so you can see the angles are labeled X, Y, and Z. So that's lowercase x, y, and z, and so that's our K, L, and M. And we've also constructed points capital X, Y, and Z. So we've intersected the blue lines with the sides of the triangle to get the lowercase x, y, and z's. Okay, so we're also using the information such as MAB equals LAC. So MAB and LAC are both given X. So you recall Chaver's theorem, it suffices to prove AZ over ZB times BX over XC times CY over Y is equal to 1. Okay, so P. Okay, so there's quite a lot going on here. So BX over XC. So what is going on here is we're trying to find the ratio of the areas of triangle ABX and ACX. And to find that ratio, we can see is the two triangles have the same altitude, so they have the same height, but the only thing that's different is the bases. So since the area of a triangle is half times base times height, when you take the ratio of the areas, the height doesn't come into the equation, so only the bases come into the equation. So you have BX over XC is your ratio of areas. And in fact, the same thing applies for the area of KBX divided by the area of KCX. So these two triangles, KBX and KCX, also have the same altitude. So the ratio of the areas is the same as the ratio of the bases. Okay, so now we have something called addendo, which is down here in this side note. It's quite a simple statement which saying if the number R is equal to A over B, and it's also equal to C over D, it turns out value R is also equal to A plus C divided by B plus D. I think it's quite an intuitive statement, even though it may not look that intuitive, and you can try putting actual numbers into A, B, C, and D will make more sense. So what's happening here is they use addendo. BX over XC is actually equal to this plus this divided by this plus this. So if we add the areas of ABX and ABK, BXK, KBX, we get ABK. So we get a larger triangle ABK. And the denominator becomes the area of ACK. And now the area of ABK, you can use the formula that uses trigonometry. So you have half AB sine C. If you recall from high school trigonometry, half AB sine C is the area of, it's one formula for the area of a triangle. So here we have half times AB times BK times the sine of, so we have beta plus Y as the area, as the angle ABK, and the area of ACK is half times AC times CK times the sine of this angle, which is gamma plus Z. Okay, so that is BX over XC. So now we have these sine stuff going on. And okay, so yeah, I can move on to the next part of the proof, which is obtaining similar expressions for, so what we found from earlier. So we found, what was it? you found bx over xc here, and that involves the sine formula. So now we can do a similar thing for the other two sides. So ay over yc and az over zb. Wait. B. So we talk similar expressions. Okay. Let's try to recall. Where's the signs? Where's the sign of the angles gone? Okay, so that is sine beta plus gamma and beta plus y and gamma plus z. Okay. So, oh yeah, we have KB over KC here. Oh yeah, okay. What's happening here? I think quite a lot has happened here. So what's happening is when you do similar expressions, the AB over AC stuff also cancel out because you have AB over AC and AC over BC and BC over AB when you have the similar expression. So these things actually, you can all cancel them out when you multiply the ratios. And in fact, you can also cancel out the sine stuff as well. And this is because, for example, angle ABK and MBC are the same because you have a beta here and a beta here. So in fact, you can also cancel out the sines here as well. Quite a lot happen in just that one step of multiplying the ratios. When you do the similar, when you multiply the similar ratios for the AY, YC, and so on. Okay, yes, yeah, now we can move on. Yes, yeah, it's just a bit confused for a second, but because quite a lot happened in this one step. So now the product of the ratios is KB over KC times LC over LA times AM over MB. Okay. So now we have to find, for example, see if we can find a ratio, how we can find this ratio KB, another expression for this ratio KB over KC. Okay, so if I can go to the next one. So now we can use a sine rule in triangle KBC, and we get, for example, KB over sine Z is the same as KC over sine Z, KC over sine Y. So it means KB over KC is the same as sine Z over sine Y. And similar expressions for the reigning ratios, you get, we'll get sine Z over sine Y times sine Y over sine X times sine X over sine Z. And just like before, it all cancels out to just get one. So P, the product of the ratios we wanted to find at the start, is equal to 1. And now using Taylor's theorem, you can conclude the AX, BY, and CZ are all concurrent. Oh, got trigonometric version of Taylor's theorem. So before we had ratios of side lengths, and now there's a second way using trigonometry to find, which is a condition for these three lines to be concurrent. And we have the angles, the alpha 1, alpha 2, beta 1, beta 2, and gamma 1, gamma 2. If the ratios of the sines of them all multiply to +1, it turns out they also, that's some condition to check if the Chavians are concurrent. And the proof can be, so you can prove it using the sine rule by applying it several times. So for example, so cx over sine alpha 1 using the sine rule is the same as AC over sine theta. If you make this angle theta, and also xb over sine alpha 2 is the same as AB over sine of this angle here is the same as 180 degrees minus theta. But sine 180 degrees minus theta and sine theta are the same, so you can actually divide these two, for example, and you end up getting sine alpha 1 over sine alpha 2 is AB over AC times CX over XB. And actually, you can make it equivalent to Taylor's theorem itself. So these AB over AC stuff will also cancel out, but the CX over XB will make it equivalent to the regular Taylor's theorem. Okay, that is a quick outline of how the proof works. That's proving trigonometric version. But to prove normal Taylor's theorem, again, you can have a look at the ratio of areas of triangles. If you remember that two triangles with the same altitude, the ratio of the areas is the same as the ratio of the bases. So that can be used to prove both Taylor and Menelaus' theorem. Okay, I think that's all we have for Taylor's theorem and concurrency and collinearity.
Awesome stuff. So thanks, guys. So I'll post the Discord and I'll post the attendance form again in the chat. If you want to, I've posted the problem set in the Discord. If you want to go over and check that out, you can jump in one of the channels and discuss one of the problems with other people. But other than that, thanks for coming, everyone, and hopefully see you again in 2 weeks.